Hello guys, welcome back to my channel. Today we're going to solve this Leetcode question which is called range sum of BST. BST is nothing but binary search tree, and in this question we are we are given we are given a binary search tree, and we need to find the sum of numbers which are between the values that is low and high. If you take a look at this example, we are given a low and a high and a binary search tree. What we need to do is we need to return the sum of the values which are in between low and high. If you look at this example, 10 is in between 7 and 15, right? So is in between 5 is not in between, so 5 is not there. 3 is also not there. Yeah, 7 is there. Okay, 15 is also there. 18 is not there. So our sum will be 10 plus 7 plus 15, which will be 32. If you take a look at this example, the low value is 6 and the high value is 10. So 10 is between the value, right? Between these two values. So it is in the range. 5 is not in the range. 3 is not in the range. 1 is not in the range. 7 is in the range. 6 is in the range. 15 is not in the range. 13 is not in the range. 18 is also not in the range. So the sum will be 10 plus 7 plus 6, which will be 23. So the answer will be 23. So it is a very easy question to solve. All we need to do is we need to traverse the binary search tree and all add all the values which are in the given range. Suppose if you look at this, suppose if we find a node value is within the range, then we can add that to our sum. How are we going to solve this? Let's look at it. Let's try to solve it using the initial brute force approach. Let's suppose, yeah, the brute force solution is, all we need to do is, we just need to traverse the entire tree and we need to add all the values which are in the given range. That's it. We can either do a pre-order traversal or in-order traversal or a post-order traversal. That's it. Okay, let's look at one example. I'm going to solve this by using pre-order traversal. Let's see how I'm going to do that. Okay, let's try to solve this example. But okay, in this question, we're having a binary search tree, and our low is 7, and our high is 15. Now I'm doing a pre-order traversal, right? In pre-order traversal, first we'll go left, then it is root, and then it is right. Left, root, and right. Initially, I'll come here. I see that 10, and this node has a left, right? So since it has a left, so I'll go left because pre-order traversal it is left, root, and right. And I'll come to this value and I see there is a left, so I'll go left. And when I come here and I'll go left, I see there is no value. It is null, right? So this will return 0. And after left, we'll traverse the root, right? So when I come to this root, I see that if it is in the range or not. It is not in the range, right? 3 is not in between 7 and 15. So I will not add 3 to my answer. And after that I'll go to right. I see that right is also null. This will return 0. Now what I'll return is 0 plus 0 plus. I will not include 3 here because 3 is not in the range. So I will return 0, right? 0 plus 0 plus 0 plus. I'm not including 3. So it is 0. So I will return 0. So we have completed left and we need to traverse the root, right? So from left I'm getting 0 and on the root I see 5 is not in the range, so I will not include 5 as well. So I'll go to right. When I come here, I'll again go to my left, which is null, so it will return 0. Then I see that 7 is in the range, right? So I will include 7. I will include 7 and I'll go to the right. This right will return 0. So 0 plus 7, which is 7, right? 7. Now if you take a look at this, the left is returning 0 and the right is returning 7. And 5 is not in the range. So I will not include 5 and I will only return 0 plus 7, which is 7, right? Then for this node, the left value is the left subtree, the whole subtree is traversed and the value is 7. Now I'm going to traverse the right subtree. Sorry. Now I'm going to traverse the root, right? I see that root is in the range 7 and 15. So I will include this thing. So 10 plus 7 is 17. And I'll go to the right. I see that for this node there is a left value. So I'll go to the left. I'll go to the left and I'll see null and this will return 0. And I see that 13 is in the range between 7 and 15. So I will include 13. I'll go to the right and this will return 0. And if you take a look at this 0 plus 0 plus 13, I'm including 13. So 0 plus 0 plus 13, which will be 13, right? Then after this, I'm going to traverse this. 15 is in the range of 7 comma 15, right? So I'm going to include this thing. 13 plus 15 is 28 and I'm going to write. I see that 18 is not in the range. I'm sorry. After 18, I'll go left, which will return 0. Then I see that 18 is not in the range, so I'll not include this thing. When I go to the right, this will return 0. And 0 plus 0 plus, and I'm not including 18, so this will return 0. For 15, it is getting 13 from the left and 0 from the right, and I'm including 15, right? So it will return 28. 28 plus 7 is nothing but 35. It is our answer. So in this way, we're going to solve this question. So what is the time complexity? Here, we are traversing each and every node once. So our the time complexity will be order of n. And what is the space complexity? Since we are not using any extra space, our space complexity will be order of 1. We're only using one variable, which will be sum, right? This sum will store this sum, right? The sum which is passing in between the recursion calls. This sum, we're only using one variable, so the space complexity will be order of 1. We can also stop here, but if you look at this thing, we are given not a normal tree, we are given a binary search tree. What is the property of binary search tree? All the values towards the left of the root will be less than root. All the values towards the right of the root will be greater than or equal to root, right? So we can use this property to solve this question in a more efficient way. Let's see how can we solve this by using more efficient. We are going the tree of a binary search tree question. Now, let's look at this example to get an understanding of how we can solve this using binary search tree. Now, here our low is 6 and our high is 10. If you look at this example, this is our low. I'm sorry. If you look at this example, we see that 10 is in between 6 and 10, right? So I'll take this and I'll come left and I see that 5 is not in the range. 5 is less than the low, right? So even if I go left of 5, even if I go towards the left of 5, I will only have values which are less than 5. So they will definitely be less than 6. So I will not, if I don't include this, I will never include this, I will never include this, right? If a particular value is less, I will directly go to the right. I will never explore the left subtree because the values on the left will be less than the this value. So that's why I'll directly go to the right. I see that 7 is in the range. So I'll go left and I'll go right, both ways. And if you and after this I'll come here and I'll go here. I see that 15 is not in the range. When 15 is not in the range, even if I go towards the right, I will only have larger values, right? 15 itself is greater than my high, and all the values on the right will always be greater than 10, right? So I will never go towards the right when my value is greater than my high. I will directly go towards the left. It is the property that we are going to use here. So let's code in, you know, for both the approaches. First we'll first we'll see the code of what I'll do is I'll create a function get some which will take a denote the low value, the high value. And if you look at here, when my root becomes null, we are returning 0, right? So it is a base case. If it is equal to null, we're just returning 0. And after that, what we're what we're doing initially when we come to a node, we're traversing towards the left and we're traversing towards the right, and then we're adding the middle values. What I'll do is some to get some of dot left. I'm going to the left with the same low and high. I'm getting the left sum. And what I'll do is I'll go towards the right as well. Right sum, get sum of right comma high. So now value equals to initially 0. I will only include this root dot value only if it is greater than or equals to, and this root dot value should be less than or equals to high. Then only my value becomes dot value. Else it will stay 0. And at the end I will just return value plus left sum plus right. And in this main function I'll return get sum of comma high. Let's try to run this. Yes, it's running fine, but we can still optimize this. Right? What is the optimization that we can do here means if my root dot value is less than my low, then I will not explore these two branches, right? I explained you here. If my value is less than the low itself, I will never try to explore these things, the left subtree. I will only explore my right subtree, right? So if it is less than low, I'll only explore and return my left subtree, right subtree, I'm sorry. If my root dot value is greater than my high, we'll only explore my left subtree. Else this will run as is. We're just adding two more conditions to make it more efficient. That's it. Look at this. It is only taking 0 milliseconds. What is the time complexity of the efficient solution? The time complexity will be order of log n, because at any point we're only what they call, at any point we're only going to one of its branches. So the worst case will be order of n. If all the values are in between the range, then the time complexity will be order of n. And if only some values are within the range, then the time complexity will be order of log n. So the overall time complexity will be order of n itself. But it is more efficient than our entire traversing of the tree. That's it, guys. If you find this video helpful, just yeah, like the video. Thank you.